Chapter 3 concerns itself with the atom. The concept of the atom is an ancient concept. It comes from ancient Greece, and it was a thought experiment where Lucretius and Democritus kind of had an argument where they said, we can clearly see that some pure objects are pure to themselves. So you could tell that if you had a lump of gold, that even if you cut it in half, it's gold all the way through. And if you had a lump of copper and you cut it in half, it's copper all the way through. And the copper and the gold are distinct from one another. And then they said, well, if we kept cutting it in half, and in fact, what would happen if we ground it down to dust? How small could we go and the gold still be gold and the copper dust still be copper dust? And they decided as a thought experiment 2,500 years ago that there must be a smallest particle on the planet, the smallest indivisible particle. And they call that the atom. And then fast forward a couple of thousand years later, and we have chemistry and physics and biology that builds on the fact that the atoms are actually there. One of the pioneers in modern atomic theory, and this predates the nuclear revolution of the 20th century, was John Dalton. And Dalton said that the atom is the smallest indivisible particle, and that everything, all matter, is made up of atoms, and that atoms cannot be created, nor can they be destroyed, and that when atoms combine to make compounds, they do so in whole number multiples. They do so in ratios. So when you take hydrogen and oxygen together to make H2O, to make water, there's exactly 2 hydrogens for exactly 1 oxygen. It's a hint there that the atoms don't get subdivided, that the atoms remain intact, and that every atom in an element is the same kind of atom. So we're going to spend chapter 3 looking at the nature of the atom itself, but where all of this came from and where it led to was a concept of reaction chemistry that we'll do in a later chapter. And basically what that gave us are 2 things called the law of conservation of mass and the law of definite proportions. So early chemists from a couple of hundred years ago, from the 1700s, 1800s, discovered that when you combine reactants together and they go on to make products, that they do so in integer, whole number, multiples. So if I took some nitrogen, this is nitrogen from the atmosphere, it's a gas, N2, it is 2 atoms of nitrogen stuck together, and I took some hydrogen, H2, that's the hydrogen gas that is 2 hydrogen atoms stuck together, and combined them to make ammonia. And ammonia is 1 atom of nitrogen with 3 atoms of hydrogen attached to it, that they do so in a 1:3 ratio, and they make 2 equivalents of this gas. Okay, so if we count the number of atoms on the left and we count the number of atoms on the right, I have 2 nitrogens and I have 3 sets of 2 hydrogens, so I have 6. And over here I have the 2 nitrogens and I have 2 sets of 3 hydrogens, so it's 6. This is the law of conservation of mass. It tells us that the atoms don't go anywhere. They have to be used. You can't destroy them and you cannot create them. And because all matter is made of atoms, this is all of the mass that's in this reaction. And so all of the mass of the reactants end up being all of the mass of the products. And the definite proportions shows up. And this predates our modern understanding of how atoms bond to one another. That if I took 1 liter of this gas and combined it with exactly 3 liters of that gas, it doesn't combine to make 4 liters. It combines to make 2 liters. Because it's not about the amount that you put in, it's about the numerical relationship. The 1 to 3 equals 2 in this case. That's something that we'll deal with in a later chapter. But it is mentioned at the beginning of this chapter as a pre-nuclear, pre-atomic understanding of that the atoms really are there, and we can tell that they're there because they are interacting in whole numbers. So for the longest time, the atom was the smallest indivisible particle. And then at the beginning of the 20th century, we split the atom. And now the atom is not the smallest indivisible particle. We have subatomic particles. 3 major ones are called the proton, the neutron, and the electron. They each play their own role in what the atom is capable of, and they have their own properties. So the proton is given symbol P. That's a lowercase p. I know I write in all caps all the time, but these are all lowercase letters. And it has mass. Now you can look in the textbook and find out exactly what the mass of a proton and a neutron is in kilograms. There's absolutely no need to know that number. What we've discovered though are that the protons and neutrons have about the same mass, and it is significantly larger than that of an electron. It's 2,000 times bigger than that of an electron. So we're just going to call it 1 atomic mass unit, AMU. So the proton, symbol P, has a mass of 1 and a charge of +1. Its location is we find the proton in the nucleus of the atom. So this is a kind of a representation, a schematic that you see that's supposed to represent what an atom is. You might have seen something similar. It turns out that atoms are spherical, and if you had an atom that was this big, about 1/10,000th of the size of the entire atom, right at the center, there's a tiny little spot where almost all of the mass is. That's the nucleus, and that's where the proton is. The rest of the atom is empty space. And what the proton does is determines what the identity of the atom is. Atoms have an integer value of protons. Hydrogen atoms have 1 proton in their nucleus. Helium atoms have 2 protons in their nucleus. Lithium atoms have 3. And I say to the students in my in-person class, have you ever seen a bicycle with 3 wheels? And sometimes they nod like, yeah, I've seen one of those. And I say, no, you haven't. Because bicycles with 3 wheels are called tricycles. Atoms with 3 protons are called lithiums. Atoms with 2 hydrogens, with 2 protons are called heliums. And atoms with 1 proton are called hydrogens. The same way that unicycle, bicycle, tricycle, changing the number of wheels changes the identity and the name of the vehicle. Changing the number of protons in the atom changes its identity. So the protons are very, very important. Neutrons, given symbol N, have a mass of 1. They have no charge. They're also found in the nucleus, and what they do is they sit between the protons. The protons carry this charge. It's a positive charge, and you might be aware that if you have positives next to each other, that they repel. So the more positives you put into the nucleus, this incredibly small space, the more repulsion you're going to generate. So you're going to need neutrons to keep the positives away from each other. And eventually, when the atoms get to be very large, around about 100 protons in a nucleus, that's when we start to see radioactivity, that the atoms are so unstable that they just spontaneously fall apart into radioactive fission. So the neutron's role is for stability, to keep the protons apart. And then electrons. Electrons are very, very mysterious things. The more we look at them, the more complicated they get. Electrons are given symbol E. They're very, very small. They're about 1/2000th the size, the mass of either a proton or a neutron. They have a negative charge, and they're found on the outside part of the atoms, and they whiz around in orbit around the nucleus at almost the speed of light. And we're going to look a tiny bit at what the shapes of the orbitals are later on. If you want to look a little bit more and you want to talk about it, I can go on and on and on forever. But let's try and keep it simple. And it turns out that if I have an atom here and another atom here, and these two atoms approach each other and they ask those important questions like, are you going to be the kind of atom that I want to interact with? Well, all of those decisions are going to be made on the outside of the atom. Well, that's where the electrons are. It turns out that electrons perform all chemistry. This is incredibly important too. Okay, so when we look at the periodic table, our book has a periodic table. Curiously, this version of the book does not have a periodic table inside the front cover or the back cover. It's usually where you can find one. But here's the periodic table. If we look at the periodic table, inside each of these boxes, we're going to find three things. We're going to find a symbol, and a symbol is either an individual capital letter or two letters, the first of which is capitalized. That's the symbol. So this Li represents lithium. Lithium is in position 3 on the periodic table. So inside the box, we get a symbol and two numbers. There is a number that is smaller and a number that is larger. The number that is smaller is called the atomic number, and it's always an integer. It's always a whole number. The atomic number for lithium is 3. And what the atomic number represents is the number of protons. So lithium has 3 protons. Then there's another number, and that number is the mass number. And the mass number represents the number of protons plus the number of neutrons. So for lithium, those numbers are 3 and 6.941, which is almost 7. It's almost 7. So if out of that 7 atomic mass units, 3 of them belong to the proton, that means that 4 of them must belong to the neutron. Okay? The other thing that the periodic table shows us, but doesn't state explicitly, is that if we know what the number of protons in an atom is by looking at its atomic number, its position on the table, and protons are positive, and atoms don't have a charge, that means that the number of pluses inside the atom must match the number of negatives inside the atom. So the number of protons in an atom is always the same as the number of electrons. So these two numbers tell me that lithium contains 3 protons, 3 electrons, and 4 neutrons. Because protons and electrons play very important roles in the nature of an atom, their numbers are fixed. But neutrons are just in there to solve a problem, to stop the nucleus of the atom from falling apart. So there's no fixed number that is the only answer to that problem. And that's where we see isotopes. Isotopes are atoms that contain the same number of protons. That means that they have exactly the same chemical behavior, but they have different numbers of neutrons, which means they have different masses. And heavy objects move slower than lighter objects. So we start to see a physical difference between them. So if we were to look at carbon, and we were to read that it had an atomic number of 6 and a mass number of 12, what we could infer from the atomic number is the number of protons, which would tell me that carbon has 6 protons. Protons are positive, electrons are negative, so if I have 6 protons, I must have 6 electrons. And then a mass number of 12 is the combined value of protons and neutrons. Well, 6 of those were protons. So 12 minus 6 gives me 6. So an atom of carbon that we call carbon 12 has 6 protons, 6 neutrons, and 6 electrons. It has 2 other isotopes called carbon 13 and carbon 14. Here's carbon 14. It has the same number of protons, which means it has the same number of electrons, but its mass number is different. It has 2 additional neutrons. 14 minus 6 puts an 8 in the middle, right here. The number that we display for the mass number on the periodic table turns out to be a weighted average of all of the masses of all of the available isotopes for that particular atom. So for carbon, on the periodic table, we see the symbol, capital C. We see it has an atomic number of 6, which means 6 protons and 6 electrons, but it has a mass number of 12.011, which means that even after you've averaged in how much 14 carbon is on the planet, most of the carbon on our planet is carbon 12. Turns out a little tiny bit is carbon 14, and carbon 14 is radioactive, and it's going to be the basis for carbon dating. And we'll come back and look at that in a separate section. As chemists, we really need to focus on what the electrons are doing. And it turns out that the electrons are really complicated and mysterious. And our book has tried to cram 100 pages worth of information down into 3. And it's just not doable. So we'll just give you the briefest explanation that we possibly can and not try to force it. So it turns out that electrons are allowed to have only very specific values of energy. They're not open to have just any amount of energy that they would like to have. Their energies are quantized. They're fixed to a particular number. And the math that underpins this is a brand new type of math. It's only 100 years old. It was invented in the early part of the 20th century. And it's called quantum mechanics. And what quantum mechanics does is it applies what look like geometrical rules to probability. And it's kind of complicated. But what it does is it actually works, and it gives us values of where we would expect to find an electron in an atom. And when we look, what the math predicts has turned out to be kind of correct. So quantum mechanics predicts the number and the shape of where the electrons are and what in these orbitals. Now it turns out that it breaks down along the lines of that awkward shape that the periodic table had. Now, the periodic table is kind of this shape, and we'd earlier said that we were going to number 1, 2, 3, 4, 5, 6, 7, 8. And that block and this block we were going to combine to call the main block. Well, this part of the periodic table, the first two groups, is called the S block, and this, groups 3 to 8, is called the P block. The unnumbered blocks in the middle are called D. And quantum mechanics predicts that there will be one type of spherical orbital that will hold the electrons in this part of the periodic table. And that spherical orbital is going to be called an S orbital. And it's capable of holding a maximum of 2 electrons. Now the P block is 6 atoms wide. And quantum mechanics predicts that there will be 3 of these kind of figure 8 shaped orbitals. These are called p orbitals. And the little diagram here is the x-axis, the y-axis, and the z-axis. So it's a 3-dimensional representation. And each of these is capable of holding a maximum of 2 electrons. So we have space for 6 electrons in the p block. And quantum mechanics predicts that the transition metals in this middle part, in the d block, their electrons are going to go in these much more complicated shaped d orbitals that are like 4-leaf clovers. They're 4-lobed clover leaves, and they're all in subtly different orientations. And each of them can hold 2 electrons, and I have 5 of them. So the D block is 10 electrons wide. Okay, that's the theory. Let's look at what a little bit of application of this is. So our book tells us that there is a thing called the electromagnetic spectrum. This is all of the light that the sun generates. It's all of the forms of energy that the sun radiates. So it's things in there like microwave and radio and ultraviolet and infrared, visible right in the middle, and gamma rays and X-rays. But the light from the sun that we can experience is what we would call a continuum. That if we put a prism up to sunlight, it would separate into all of the colors of the rainbow. And there's no gaps. It just works in a continuum. Now, when we take an atom and we either excite it with lots and lots of energy, or we burn it in a flame, well, what it does, so here's a rainbow, this is a continuum, this is all of the light from white light from the sun, and then above is the emission spectrum from an atom, and you see that it's mostly dark, but then there are just allowable bands of energy. These are the quantized bands of energy, and it reveals itself as frequency or wavelength. Okay. Well, what that means is no 2 atoms are exactly the same. And if I were to look at the color of light under something called a diffractometer, I would be able to tell one atom from another. And that is the basis of an analytical technique called atomic emission spectroscopy. And that's a forensic tool, and we'll talk about that in its own little place later. Electron configuration is a way of transmitting to another person the information about all of the electrons that an atom has. It's a shorthand, it's a code. And I'm going to call this part of the periodic table S, this part D, and this part P. So groups 1 to 2 is S, groups 3 to 8 are P, and the ones in the middle are Ds. We're not going to get to those. So what I would do, if somebody asked me what the electron configuration for nitrogen is, nitrogen is in the second period, remember periods are the horizontal rows, and is in group 5. Well, it contains the electrons from hydrogen through helium and lithium and beryllium, and the electrons for boron and carbon before it puts this last electron in. So we would say that the electron configuration for nitrogen starts in period 1, and in the S block there are 2 electrons. So we start by 1s2. That's the period number, the block, and the number of electrons. I've got 2 electrons in that first period. And then I move on to period 2. It's still an s orbital, and I have the electrons for lithium and beryllium, 2s2. And then still in the second period, but now in the p block, boron, carbon, and nitrogen, so 2p3. The electron configuration for nitrogen is 1s2, 2s2, 2p3. There are 2 electrons in the first period that belong in an s orbital, spherical orbital. And then in the second period, there are 2 electrons in another spherical orbital. And then still in the second period, there are 3 electrons in p-shaped orbitals, the figure 8 shaped orbitals. This is our shorthand. Let's do another one of those. This time, let's look for what the electron configuration of silicon might be. Silicon is right here. It's in period 3, periods horizontal, group 4, groups are vertical. So it contains all of the electrons that preceded it, plus the one for its own box. Starting in period 1, I have 2 electrons in an s orbital. And then I have 2 electrons in the s orbital that belongs to period 2. And then I have all 6 electrons that belong to the p orbitals in period 2. And we read the periodic table, left to right, top to bottom. And once I've finished period 2, I can start period 3, and I've got 2 electrons here in an s orbital in period 3, and then aluminum, and then silicon. So 3p2. Silicon has 2 electrons in an s orbital in period 1, 2 electrons in an s orbital in period 2, 6 electrons in p orbitals in period 2, 2 electrons in s orbitals in period 3, and 2 electrons in p orbitals in period 3. The superscripted numbers, those are the numbers that actually represent the total number of electrons. And if you add them all together, you get the total number of electrons. 2, 4, 10, 12, 14. And we find that silicon is position number 14 on the periodic table. It has 14 protons and it has 14 electrons.